Okay, welcome to section 11.4, comparison test. And there's actually two of them, and one's pretty easy. The other one requires some fairly sophisticated algebra sometimes. The comparison test, or tests, are used when you have a complicated series that actually kind of looks like one that's uncomplicated. So let's look at uncomplicated. The series from I equals 5, 1 over I squared to infinity. This is a P series. It converges because the P equals 2 is greater than 1. You can prove this by the integral test, or you just quote the P series test. This adds up. In fact, I believe it was Gauss that actually calculated what it adds up to, which is unusual. Again, I want to point that out. We don't frequently know what these things add up to. Now, this is a useful tool to know that what appears to be quadratics in the denominator are things that are going to converge. So then one would ask about, well, what about this? Or what about this? Do these things converge or diverge? Well, first off, this is a quadratic function in the denominator. So is this, so is this. They all look alike for that reason. Now, I'm going to demonstrate how the comparison test works by demonstrating a very simple fact that's involved with inequalities. So let's begin with the basic inequality of positive numbers, a less than b. So if I divide both sides by a, because it's positive, the inequality doesn't change, and we get 1 less than b over a. And now if I divide both sides by b, because it's positive, it doesn't change. And so 0 less than a less than b says 1 over b is less than 1 over a. Well, that's interesting. When you have bigger numbers than their reciprocals are smaller. So let's look at that one series I wrote down, the sum from n equals 2 to infinity of 1 over n squared plus 4n. I'm not sure if that's what I wrote. Off to the side here I want to note, n squared plus 4n is bigger than equal to n squared because we've added a positive number to the n squared. Well, b is bigger than a. b is bigger than a. So 1 over b is less than 1 over a. So 1 over n squared plus 4n is less than or equal to 1 over n squared. Well, that means that every term of this sum is smaller than every term of this sum. And this one is known to converge. Therefore, we conclude this converges, which means we might want to add it up. Convergent series that we know about help us find other convergent series. Now, the more convergent series we know, the more we gain, and the more we can use these comparison tests with other ones. Now, the other way around is divergent. So first off, I'm going to write down the convergence test for convergent series. Suppose b sub n converges and a sub n is less than or equal to b sub n for all n greater than or equal to some fixed value. It's okay if this one's bigger for a short time, but after a while it's got to always be less than this one. It's like catching up to your older brother's height, and once you get beyond them, you'll probably be taller than them forever. So what does this say? It says that the sum, and now I'm going to suppress the index. I'm going to not write where it starts, and I'm not going to write that it goes to an infinity. The sum of a sub n converges. It inherits the convergent property of b sub n because a sub n was smaller. Now we need these things to be positive, otherwise you could add up some huge negative numbers. Now the other side of this is suppose b sub n diverges, and a sub n is bigger than or equal to b sub n bigger than or equal to 0 for all n bigger than or equal to some fixed value. Then, well, you're bigger than a divergent series, the sum of a sub n diverges. Now, this is extremely useful to have a new divergence test, so we know if the terms don't go to 0, it diverges, but we actually also know that the sum of 1 over n diverges, so now we might be able to find some other things that diverge. Now, algebra can get tricky with these. Let me give you an example of a funny quadratic. That's a quadratic in the bottom. But do you have any reason to believe that n squared minus 6n plus 1 is going to be bigger than or equal to n squared? In fact, it might be the case that it's always less than a 2 of it because it was subtracted 6n. So we might not have this. But here's a good trick. I bet we can prove that it's bigger than or equal to like half of n squared or a third of n squared. Now, how do we discover that? That's kind of hard. So you just make some guesses. So I'm going to guess that n squared minus 6n plus 1 is actually bigger than or equal to 1/2 of n squared. Now, the reason I guess that is that 6n, not very big compared to n squared. So how do I go about proving that? Well, why don't I just write that down and manipulate it and see if it says something that I know is true, and then see if I can work backwards. So if I believe this, then I would believe that 2n squared minus 12n plus 2 is bigger than or equal to n squared. These are the same fact. And I subtract n squared from both sides. N squared minus 12n plus 2n is bigger than or equal to 0. Then I'm going to add 12n both sides. N squared is bigger than or equal to 12n minus 2. Now, do you believe that? Actually, let me write it a different way. Let's not write it that way. Let's try this way. N squared minus 12n is bigger than or equal to minus 2. Do you believe that? Well, I believe it because of the following fact. I look at this and I say, clearly, n times n minus 12 is positive. So I'm going to go backwards in the following way. Ready? Let n be greater than or equal to 12. I know this starts at 3, but we only need to prove it beyond a certain point. So n is going to be bigger than or equal to 12. Then n minus 12 is positive, and n is positive. Threw some information away there. Now the product of two positive numbers is positive, and 0 is bigger than or equal to minus 2. And I've just arrived here. So that says that n squared minus 12n is plus 2 is bigger than or equal to 0, and I've arrived here, and now I can add n squared to both sides. And I've just reached here, and now I'll divide both sides. Oops. Divide both sides by 2. And now I can use the fact that my denominator is bigger than this, so the reciprocals are less than 1 over 1/2 of n squared, which is 2 over n squared. And I happen to know that the sum of 2 over n squared converges because the 2 comes out and 1 over n squared is a convergence sequence. Therefore, the sum of 1 over n squared minus 6n plus 1 has convergence as well by the comparison test. This is the hard way to do things. But in reality, what it says is when things are quadratic in the bottom, If you compare them to a quadratic, you're going to be able to make it work. This is a kind of a cool way to go. So let's do a problem where we don't necessarily see where it's coming from. So let's take the sum of n squared over n to the fourth plus 2n plus 1 from 1 to infinity. Let's determine what's going on. Well, first off, this is approximately what we call a dominant term, n to the fourth on the bottom, n squared on the top. I think this looks a lot like 1 over a quadratic. So off to the side, I think, I'm going to get this thing less than or equal to 1 over, and I don't know what number I want to put there. So here's a good trick as well. I'm going to put 1 over an squared. Now, these are positive, so now let's cross multiply or multiply both sides by an squared and then multiply both sides by n to the fourth plus 2n plus 1. But I'll get an to the fourth less than or equal to n to the fourth plus 2n plus 1. And so I'm going to put I'll just put 0 less than or equal to n to the fourth minus a n to the fourth plus 2n plus 1. Now, this is already positive. How do we guarantee this to be positive? Well, we know that this positive and a positive and a positive will be positive. So this fact will be true. It says this is true. It says this is true. It says this is true. And we just have to pick a nice a. How about a equals a half? And that says that 1/2 n to the fourth plus 2n plus 1 is positive. And now we work our way backwards. So what do we have? We now have that the sum of n squared over n to the fourth plus 2n plus 1 is less than or equal to the sum of 2 over n squared, which by the p-test converges. Therefore, this one converges. Now, some people don't like having numerators at all, so they force everything in the denominator. So n squared over n to the fourth plus 2n plus 1. You can just multiply top and bottom by 1 over n squared, and you'll get 1 over n squared plus 2 plus 1 over n. Now, that's a really good technique because that's positive, so this is less than or equal to just 1 over n squared because this is bigger than n squared, therefore its reciprocal is less. That's a nice, slick way of doing things. It also kind of tells you what's going on right away. This is a perfectly good argument to go from here to here to there. Common one, a insightful algebraic attempt. Now, we often talk about what a series looks like. So, what does this series look like? Well, the top, for large values of n, you put in 100, this is 10, plus 2 is 12. You put in a 10,000, this is 102. This is the dominant term in the top, and this is the dominant term in the back. So we'll often say it is like or approximately root n over n squared, which is n to the 1/2 over n squared, which is 1 over n to the 3/2, and that's a p series, p bigger than 1, which is convergent. So this should be easily comparable to that. Turns out it's really not. It's kind of hard. It's kind of hard to prove this, that it's less than or equal to some a over n to the 3/2. Now notice I put the a in the top this time. I could have put the a in the bottom. Doesn't matter. You put the a where you like. You want to figure that out. It gets algebraically difficult. And algebra is not always the best way to do things. So here was some algebraic difficulty, and it turned out an insightful technique was a little bit quicker. Well, there's another comparison test. This is called the limit comparison test. And the limit comparison test is so cool because what it does is first you figure out what something looks like and you see what this is. And the limit comparison test says, given an and given bn, and you can calculate the limit as n goes to infinity of an over bn. And most importantly, if this limit isn't 0, then the sum of an and the sum of bn behave the same. It means that if this converges, that converges. If that diverges, that diverges. If this diverges, that diverges. If this converges, that converges. You just need two series that are alike. Well, I'm going to do that here. I have an, which is root n plus 2 over n squared minus 7, and I have bn, which is 1 over n to the 3 halves. Now, I know this is convergent. So I'm going to now calculate what is the limit as n goes to infinity of the square root of n plus 2 over n squared minus 7 divided by 1 over n to the 3 halves. Now, to do that limit, I just have to get the fractions down to one fraction, not two. And I was dividing by 1 over n to the 3 halves, so invert and multiply. N to the 3 halves times n to the 1 half is n to the 4 halves, which is n squared. N to the 3 halves 2 is n to the 3 halves, 2 n to the 3 halves. N squared minus 7. Now, that's a quadratic over a quadratic, so now we use the standard Calc 1 trick of multiplying by 1 over the power of the denominator. 1 over n squared times n is 1. 1 over n squared times 2n to the 3 halves is 2 square root of n. 1 over n squared times n squared is 1. 1 over n squared times minus 7 is 7 over n squared. And now, as n goes to infinity, this goes to 0, this goes to 0. We get 1, which is not 0. And we have just proved that the behavior of a sub n equal root n plus 2 over n squared minus 7 is the same as bn, which is 1 over n to the 3 halves. And that is convergent, which says we just discovered that's convergent. That's called the limit comparison test. And the limit comparison test basically says you can look at things and figure out what they're like. Well, I'm going to give you a list of facts. Exponentials, they're bigger than polynomials. Polynomials are broken down that n plus 1 is bigger than n minus 1. So if you have a quadratic or a cubic, it's bigger than n, etc. And then comes constant functions, which in that group is sines and cosines. They are basically just pretty much bounded by between their amplitudes. So they're constant. They vary, but they're like constant functions. Now, what's above a constant function but beneath the polynomial? Well, you wiggle in between here some logarithms. They're bigger than constant functions but less than polynomials. And then things like square roots of n, they kind of wiggle in there. You have the orders. Well, the things that are bigger, when you divide by them, make things smaller. And so you use these to compare, and you want to just make sure the denominators, the numerator. Usually if this is bigger than that, you've got a good chance to converge, but in the polynomials it needs to be bigger by more than 1 degree, or if you're using powers, it's got to be more than 1 degree. So this gives you an idea of how to attack a problem. So ready? Let's suppose we do this. The sum, the absolute value of the cosine of 5k plus 2 over k squared minus 8k equals 12 to infinity. What would I do with that? Well, first off, the top is a cosine function. Now, even if it oscillates, it doesn't oscillate bigger than 1 or minus 1. So the numerator looks like a constant. The bottom looks like a quadratic. So I'm interested maybe in proving that the limit of this being compared to a quadratic might work. Or it turns out if that limit doesn't work, maybe something slightly smaller than a quadratic but bigger than a linear in the bottom can show that this one is convergent. So I'm going to do the following. Take cosine of 5k plus 2 is less than 1. Cos squared minus 8 over k squared minus 8. But this one, let's say less than equal, might be equal. This one, by doing the limit comparison to 1 over k squared, this converges, therefore this converges, and now by the straight-up comparison test, this converges. So I can use multiple tests to make things happen. All right, and that is section 11.3.